scientific collaboration in human history, both in the scale of the detector and in the size of the collaboration, the number of people involved. We've got thousands of scientists from programs all over the globe, which is how I got involved, actually. I'm 24 years old, did my undergraduate degree in physics at Duke University, went on to the doctoral program over in Illinois, and if you're interested in physics, there are lots and lots of different areas in physics. Physics talks about small things, talks about enormous things in space, talks about very, very dense things, condensed matter, how that works. But if you're interested in really small, really high energy things, if you're interested in particle physics, the place to be right now is over at CERN, at the Large Hadron Collider, where we smash these very small particles together really, really fast. Now, we said correctly that the protons we're smashing move at just about the speed of light. To give you a sense of just how fast that is, way back 40 years ago, when the guys with the Apollo program flew up to the moon, that took them about 3 days to take a rocket ship from here to the moon. How fast do you suppose light goes from here to the moon? Any guesses? Yeah?
10 seconds.
Very close, actually, on the order of magnitude. It takes you about 3 seconds to go to the moon and back if you're moving at the speed of light. So that is outrageously fast, faster than we can comprehend. That 17-mile circular track the protons are going in, your proton actually goes around that track upwards of 10,000 times per second. So this is very, very fast. An outrageous amount of engineering expertise went into making this possible. The actual detector I work on, Atlas, where we look at the proton smash, it measures by 20 meters wide, 20 meters tall, 40 meters long. So around the size of my house. Outrageously big. It is just insane to me that we were able to build something so big and so complex and have it work as well as it does. So, any questions about like what I do, what the detector is, that sort of stuff? Yeah?
So since July 4th, 2012, the Higgs boson was confirmed, so what objectives are you attempting to achieve at the moment?
Right, exactly. So he mentioned the Higgs boson, which was really, really exciting when we found that because we had this standard model of particle physics since about the 1960s, where the math predicts all sorts of how these tiny little things interact. And this theory was more successful than any business being. Experimentally confirmed over and over and over again. But it took half a century to find the last piece of that puzzle, Higgs boson, which is a really tiny, really heavy little particle that, through its interactions with everybody else, gives mass, gives weight to everything else in the universe. If you didn't have this Higgs boson or something to do its job, you wouldn't have the world as we'd know it. You'd have everything just fly apart into nonsense. And since we have seen the Higgs boson, or at least something that looks a heck of a lot like the Higgs boson ought to look, the good question is, what are we looking for now? Things going on into run 2, the big, big fad out there right now, is something called supersymmetry. The idea of which is that all of the elementary particles we know about, let's talk about particles actually. What particles have we heard of? Any ideas on that? Sure. Quarks, exactly. Quarks are these tiny little guys that go on inside of protons and neutrons. Have we heard about protons and neutrons before this class? Yes. It's kind of funny that we even have protons and neutrons, because we know, of course, about atoms, which make up all of our macroscopic matter, and the word atom actually comes from the Greek atomos, which was indivisible. So once upon a time, we named atoms when we discovered them because we imagined that was as small as things were. They were indivisible. They were unbreakable. They were the building blocks of everything else. And then you go on a few decades, and it turns out the atom has a closet structure. The atom has protons and neutrons and electrons smeared around them. while that was the most elementary particle. Then we look further, it turns out your protons and your neutrons have quarks and gluons buzzing around inside of them. So there's this whole fascinating inventory of tiny, tiny, tiny little particles that build up everything else. I see we've got a periodic table up there of the various elements. You can make a similar catalog of your subatomic particles, where you've got 6 flavors of quarks with 3 colors apiece, and you've got 6 flavors of leptons. These guys make up all the matter. You and I, we are quarks and leptons. Then the quarks and leptons talk to each other with these other particles called bosons. Photons, for example, allow electricity to work. The W and Z boson have something called the weak force. Strong force has the gluon, which holds your quarks together in the protons and the neutrons. And of course, you have your Higgs boson, which gives mass to everything else. So going back to supersymmetry, the idea there is, okay, we've got all these cool particles we know about, but there are some questions left over. For example, to make the Higgs boson work out, you actually need a lot of mathematical coincidences to happen, basically, so that the contributions from all the particles we have add up and more or less cancel each other, so that your Higgs coupling doesn't go like off to Mars and make everything super duper heavy and crazy. So right now, we just look and say, wow, it's mighty fortunate those things cancel. As for why that is, one theory is supersymmetry, which says that for all the particles we know about, they have a hidden superpartner hiding off at some crazy high energy rate, where once upon a time, the particles and the superparticles were more or less indistinguishable except for their spin. Then something happens, supersymmetry breaks, and now we have a world made out of particles, while those superparticles out there are too heavy to be seen under normal conditions. So one hope is, at something like the Large Hadron Collider, where we're smashing these protons together with energy 1,000,000 times bigger than your average nuclear fusion reaction in the sun, the idea is with that level of energy, maybe, just maybe, you'd be able to see that lightest supersymmetric particle. And that is really exciting because supersymmetry also comes in when you talk about dark matter. Has anybody here heard about dark matter? Let's, what do we know about dark matter? Yeah? Does anybody want to say anything about dark matter? Yeah, go for it.
It does not interact with light, but does keep the unit of the galaxy from ripping itself apart.
Exactly. It's dark, sounds spooky, but it's dark just in that it doesn't interact with light. We look out there in space, we see stars, we can see dust, that's all fine. We don't see dark matter. Not with our eyes anyway, not with our telescopes. How we see dark matter is looking at the gravitational interactions of the galaxies, the superclusters out there. We can measure through techniques like gravitational lensing, or looking at the angular momentum of your galaxies, that universe is a lot heavier than what we can just see. So the question is, where is all that extra mass? The catch-all term for that is dark matter. One possible candidate for dark matter are these lightest supersymmetric guys that couldn't decay down to regular matter, that wouldn't interact with light, that could be just floating out there in space, and potentially seen in collisions in our detector. So that's one big thing we're looking at next run is maybe experimental confirmation of supersymmetry. Other questions? Yeah?
Speaking of dark matter, does it ever end? I'm just thinking right now,
Mm-hmm.
like, there's dark matter and space is humongous.
Yeah.
I can't imagine how many like dark matter things are there.
Oh yeah, it is outrageous how big space is. As far as whether space actually ends, I can't tell you that. Like we can see to the edge of space, but that edge is just determined by how far away light could travel in the time since the Big Bang. So we can only see out as far as light has been able to travel. But that doesn't mean there's not more out there. As far as the dark matter, whether we talk about the extent of it in space, whether it ends in time, the hope is that dark matter doesn't decay down to anything else. It couldn't. If it's still out there, if it could decay down to regular matter, we wouldn't have dark matter anymore. We've had billions of years for it to decay down to electrons or photons or stuff we could see. So the idea of dark matter is that it's, they say, R parity conserving. That is, it can only annihilate with other bits of dark matter. Otherwise, it needs to stick around to explain the fact that we still see it out there. Other questions?
I have some
Yeah.
questions for you. What kind of educational path did you start with? You think about like 7th grade. What kind of pathway did you start going into?
It took me a little while to get onto physics, actually. I always liked science. I always liked all sorts of different areas of school. When I was really little, I was going to be a lawyer, and then realized I didn't have the ethical flexibility for that. So then in high school, I took all sorts of AP classes, was really big on debate, and at the time, I had a really cool teacher, his name was Larry Dukridge, taught my AP chemistry course, and it was just fascinating to think of these tiny little things you could never see with the naked eye, but the little subtle interactions of them give us everything else in the world. So I had an idea there. I took a wide variety of AP courses in high school. That's definitely handy if you can set a couple of those aside, partly because they give you college credit at some schools, and partly just because the extra rigor of it can help you prepare for college. Going into university, at first I thought I wanted to do chemistry because AP chemistry was so cool. I did organic chemistry and just decided it wasn't for me. There were lots and lots of reactions you need to memorize in Orgo, whereas I was more interested in calculating things, working out those sorts of puzzles. So come my sophomore year, I decided, hey, I should look into physics, electricity, and magnetism, because my high school, I didn't do any of them. I just did mechanics, like gravity, momentum, cars smashing together, that sort of thing. So I decided I'd like to look into E&M. I had an awesome time with that course and kind of decided to throw myself into the physics program from there. And since then, that's been 6 years, haven't looked back. So you do have some time to kind of figure out where you want to go. Like me, I didn't know I was doing physics until my sophomore year of college. But I would encourage you to work your hardest at whatever you're doing right now so that you can keep your options open. Like the AP science classes I did in high school definitely didn't hurt me going forward, even though I didn't know that they were going to be like my ultimate educational destiny at that point. Does that sort of address your question?
Mm-hmm. And then how did you get selected to work at the Hadron Super?
So when I was, I think it was between my junior and senior year of college. At this point, I was with the physics program, working toward the physics degree. I wanted some sort of experimental experience at that point. So I spoke to my advisor, who worked in particle physics, and she recommended me to take a trip over to Europe for a month in the summer to work at the Large Hadron Collider. If you're interested in really small things, going really fast, smashing really loud, that's the place to be right now. And they've got scientists from programs all over the world, all over the United States. So if you are interested in particle physics, you go to college for particle physics, there are definitely opportunities that they can get you in that sort of program. Like me, I went over with half a dozen other students from my year. I want to say, if you're interested in working on Atlas or on CMS, and you go to college for particle physics, they'll find a way at some point to get you over there. Like, it's an awesome opportunity, but it's not super duper exclusive within the field. Like, I met people over there from all over. So the slots are definitely there for, I want to say, anybody who wants it, who has that background.
And did you have to have a foreign language in your background in order to be able to be selected for that?
Not at all, actually. I went over, didn't speak a word of French, speak maybe a word of French now, so it's not necessary. It can't hurt you to know in Geneva lots of French over there. Like further in the north in Switzerland, that's German. Geneva, the area where CERN is, they speak more French, so it can't hurt you to know French. But the good news is they had so many foreign scientists bringing our foreign scientists money into the area that they're more or less acclimated to an international community. You can get around the CERN campus speaking English. If you're living in France, some French wouldn't hurt, but you can skate without it. At least I have so far.
And what, I don't know, are you at liberty to talk about projects that you're working on?
Yeah, I
Okay.
can talk vaguely about stuff.
Okay.
So what I'm looking at are, they call them saturated cells in the Atlas tile calorimeter. The actual Atlas detector, that great big old 40 by 20 by 20 meter thing I was telling you about, is made up of a whole bunch of different subsystems, each of which looks at a certain sort of particle. So you smash the protons together in the middle, and outside that, you have an inner detector that tracks where the particles are going. Then you've got an electromagnetic calorimeter that looks at your electrons and protons. And outside of that, you have a hadronic calorimeter to look at your heavier guys, to look at your protons, your neutrons, your jets, that sort of thing. So I work most closely with the hadronic calorimeter, also called the tile calorimeter, because it's made up of
Hello,
a whole
elementary
bunch.
students, sorry about this interruption. I am going to announce the Franklin Firebird t-shirt winners for today. The SEO has generously offered
This
to
is
a
donate
whole bunch
ice
of
cream for
scintillating
next
tiles,
week's party
which are really
to the
cool when
winning
you look at
class
them. It
of
looks
each grade level.
basically like a
So
little
in
pane of
kindergarten,
glass.
let's
But
give
if
a
you look at
round
the
of
sides of
applause
it,
to Mrs.
it's this
Ellsworth's class.
bright blue color,
First grade,
because light hits the
Mrs. Jackson's
scintillators,
class.
and it gets
Second
beamed out of
grade,
the
Mrs.
sides.
Spencer's
You
class.
tap it up and you detect
Third grade,
it. So what
Miss
I'm
Plockett's
looking at
class.
is,
Fourth grade,
we
Mrs.
had a
Cooley's class.
guess about how much
Fifth
energy
grade,
you'd
Miss
see in
Jackson's
any
class.
given tile,
And
in
finally,
any
sixth
given
grade
cell.
is
We
Miss
guessed,
Carr's class.
like, what should the
The
energy
overall
tolerance be
winners
for
this
these? And we built
week
the test.
for primary,
We
Mrs.
figured you'd
Spencer's
have
second
maybe
grade,
a
and
couple
for
of events
intermediate,
over the
Mrs.
course of the
Louise,
first
fourth
run
grade.
where the
Thank
energy
you
of the cell
everyone
would
for your
be too big to measure.
participation, and we hope that you
At the
enjoy
end of the long, at the
day.
end of long
Just a note
shutdown,
that
we go
because
back,
it is
we
extra
look,
early, we
you
will
actually have
follow
hundreds of
rainy day
events
schedule
where the
after
energy is
this
too
for
big
this
to measure.
afternoon.
So one of
And
my
please
projects right
be
now
aware in
is
process
looking
that
at
there is going to
these
be quite a
cases
few
where
calls
the
for
cell
change
was
in
saturated. The energy was
pickup
so
and
big,
buses
I just maxed out, and you're not sure
so
what happened.
Get ready
Our
for
first thought
those.
was, is
Thank you
this
very
something
much.
wrong
We'll
with
talk
the
to you later.
equipment?
Bye.
So you've got a program you can look at where you pull it up on your computer screen and you can see the tracks of the particles and the energy depositions in the cells. These are things that are too small and too fast to ever actually see, and yet you can reconstruct a visualization from what the computer sees. So you can look at the electrons and the jets and all these fascinating little guys that make up everything. So looking at the event viewer, it looked actually like it wasn't a problem with the hardware. It's some actual physical phenomenon that is saturating these cells. So now the question for me is, what's going on here? So that's how Atlas works. You have thousands of people looking at thousands of different little physics questions, where you can find anything within the realm of particle physics. You have theory guys who put out a bazillion different papers about different phenomena we're looking at going forward. And then, of course, you need a core of people to go look for these phenomena, see if they're there, and if they're not, put exclusion limits on them that say we couldn't find them within this range. Then you have people that measure various things. Like the project I'm going to work on after the saturated cells is looking at the boosted top cross section. How many top quarks you get out of these collisions. The top quark is really interesting actually because it's a quark, most of which are even smaller than the proton. The top quark is super duper heavy. So heavy, in fact, that this one quark is about the same mass of a whole atom of iron. So it is outrageously massive. And that's really, really interesting because it's so heavy. It has a bunch of possible implications on the frontier of physics, where you can do a measurement of the top core cross section and help nail down some of the things we already know about the standard model, test the standard model to it, and at the same time, maybe run into something crazy out there we haven't seen or even imagined yet.
Attention teachers, a couple messages. First of all,
questions
I
about
need you
physics,
to
about my
please
career
check your
path?
email.
Yeah.
I sent you an email that I need you to look at immediately. And then I also need
Okay, so
students to
graviton,
please
that's a good
come
question.
to the office.
We know about gravity, that's the force we're probably most familiar with in our daily life.
Lamar Kevin Crosby.
There we go,
Jacqueline
gravitational
Malone,
interaction between the Earth and the paper.
Wells. Oh, and
Gravity
Claire
is
Brown.
interesting
Please
because
come to the
despite
office.
being the most in-your-face
Desiree
force,
Farnsworth
it's actually
as well.
the weakest.
So if
Trillions
you
and
could
trillions of
please
times
come to
weaker
the
than,
office,
say,
that would be great. Thank you.
electromagnetism. For example, if you take a magnet, you can run it over a paperclip, and the magnet can pull that paperclip into the air, even as the entire Earth is using its gravity to try to pull the paperclip back. So gravity is the very weakest force, and it's also interesting because it's the only force that's not part of the standard model. That I was telling you about the bosons, like how the photon gives you electromagnetism, or the gluon gives you the strong force. We don't have gravity included in the standard model, but if you were to talk about gravity in particle physics terms, you'd have a graviton, which is some sort of new particle that mediates gravitational interactions. Thoughts about the graviton for the LHC? To my knowledge, the graviton is likely to be outside of the energy range we can see with the LHC. It's my understanding, at least, that you need to go way, way, way more energetic before you start seeing quantum gravitational effects. Most of what I know about graviton searches are looking at gravitational waves out in space. So that's something that is covered in theory territory, but it's probably a few experimental upgrades away before we can see it in the LHC, at least to my knowledge.
Alright,
Yeah, definitely. Yeah.
How do you know which particles to smash together?
We use protons at the Large Hadron Collider. Earlier colliders might have used electrons or electron-positron collisions. The LHC uses protons, and as far as the actual collisions, you need a charged particle, is one way we decide. Electromagnetic charge, electromagnetic interactions is the only practical way we know of to accelerate these particles. So right now we use protons because they're electrically charged and because they have composite structure. They have quarks and gluons splitting around in them that are actually what collide in the collisions. All right, thanks all so much for having me.